This video is on the mean and standard deviation of a binomial random variable. Okay, so we have not done any problems like this, but I'd like you to take a look at these two examples and give an initial gut reaction. So our first one, a coin is flipped 20 times. Let x be the number of heads in 20 flips. What is the most likely value that x will take on? And part two, a six-sided die is rolled 15 times. Let y be the number of fives rolled. What is the expected value for y? So take a pause, think about this. What is your best guess? Okay, so we've got this coin. It's flipped 20 times. And so, what's the number of heads you would expect? Well, in each flip, there's a 50% chance, a half chance of getting ahead. So 20 flips times 1/2 is 10. That is, in fact, the mean for a binomial random variable. The mean, or the expected value, is the number of trials times the probability of success in one trial. So here we've got 20 flips, 20 trials. 1/2 is the probability of what we're looking for ahead happening in a single flip. So the n, the number of trials, 20 times 1/2 equals 10, is in fact the mean or expected value for this binomial random variable. And similarly, if we're looking at this six-sided die being rolled 15 times, if y is the number of fives rolled, that's also a binomial random variable, where the number of trials n is 15, and the probability of success, the probability of rolling a 5, is 1 out of 6. So the mean for this binomial random variable y is 15 times 1/6 equals 2.5. Note, this is not an actual value that we could get if we rolled the die 15 times. We could get 2, we could get 3, but 2.5 fives is not possible. So remember, when we talk about the expected value, that's the mean or expected value. That's where the distribution balances. That's the weighted average, but it might not actually be a value that the random variable can take on. So we could actually get 10 heads in 20 flips. We could not actually get 2.5 fives in 15 rolls. But that's, again, saying it's the mean of the distribution. It's the center of the distribution. So we'd most likely get, the most likely values would be 2 or 3 rolls. Okay, 2 or 3 fives in 15 rolls. So our formula for the mean or expected value of a random variable x is that the mean or the expected value of x is n, the number of trials, times p, the probability of success, for a binomial random variable. And its standard deviation, sigma, is the square root of n times p times 1 minus p. So in these two examples we have, the mean, again, as we saw, for number of heads in 20 coin flips is 20 times 1/2 is 10. Our standard deviation, the measure of how spread out the data is the square root of n times p times 1 minus p. Number of trials, 20. Probability of success, 1/2. 1 minus 1/2 is also 1/2. And if we throw that into a calculator, we get 2.24 for our standard deviation for that binomial random variable. For the binomial random variable y, number of fives in 15 rolls, as we saw, our mean or expected value for that random variable is number of trials times probability of success is 2.5. And our standard deviation is sigma is equal to the square root of number of trials, 15, times probability of success in one trial, 1/6, times 1 minus p, 5/6. And if we throw that into a calculator, we'll get a standard deviation of 1.44. Okay, so that is finding the mean and standard deviation for a binomial random variable. Again, I'm going to give you another problem without telling exactly how to do it, but I'd like you to think back to how we've answered this question based on previous material. A coin is flipped 100 times. There are 42 tails and 58 heads. Is this an unusually low number of tails? Justify your answer. So to think about this, think about how have we defined unusual so far in this course? In what ways have we said when a value is unusual? How can we tell? So think about that, pause again, and we'll talk about it together. Okay. So we've defined unusual in a couple ways. One was that a value at least this extreme occurs less than 5% of the time. That was one way we defined unusual. Something to note is that this at least this extreme idea is important. So at least this extreme, that's an important idea. Why is that? So even the most likely value might have a probability of less than 5% as an exact value. So for example, if we were thinking about 1,000 flips instead of 100, in 1,000 coin flips, 500 tails is the most likely outcome. However, the probability of exactly 500 tails in 1,000 flips is 2.5%, 0.025, which is less than 5%. Does that make it an unlikely event? No, it's the most likely possible outcome. But what we want to look at is the probability of something at least this extreme. The probability of 500 or more tails, the probability of at least 500 tails in 1,000 flips is more than 50%. This is also equal to the probability of 500 or fewer tails. So this is a very likely event, something that at least this extreme happens more than half the time. So we would not consider this event, 500 tails in 1,000 flips, unlikely, even though its exact probability is less than 5%. When we say at least this extreme, we say what's the probability of like 500 tails or more, or in this case, like 42 tails or fewer. Okay, so that was one way we talked about unusual. Another way we talked about something being unusual was if it is a value that is 2 standard deviations above or below the mean. And that is the definition we'll be using here. And finally, if it has a z-score greater than +2 or less than -2, these are really exactly the same thing. So 2 standard deviations above the mean, remember a z-score is the number of standard deviations above or below the mean. So a z-score greater than 2 means 2 standard deviations above the mean. A z-score less than -2 means 2 standard deviations or more below the mean. So these two are actually the same thing, just different ways of expressing it. And similar here, this 2 standard deviations above or below the mean is based on this 5%. More than 2 standard deviations outside the mean is something that occurs less than 5% of the time for normally distributed data. Okay, so this is what we'll be using right here. Is the value more than 2 standard deviations above or below the mean? And we know how to calculate the mean and the standard deviation, so we can figure this out. Okay, so let's do that. So we have a coin that's flipped 100 times, and we want to say, okay, what's the mean and standard deviation for the number of tails in 100 flips? Our mean is 100 times probability of success 1/2. That's 50. Our standard deviation is the square root of n times p times 1 minus p, square root of 100 times 1/2 times 1/2, and so we get a standard deviation of 5. So 2 standard deviations below the mean, that would be the mean minus 2 standard deviations, is 50 minus 2 times 5 is 40. And the mean plus 2 standard deviations, the mean 50 plus 2 times the standard deviation of 5 gives us 60. So that means an unusual value for this distribution would be less than 40 tails, more than 2 standard deviations below the mean, or more than 60 tails, more than 2 standard deviations above the mean. 42 tails in 100 flips is not unusually low because it is not 2 standard deviations above or below the mean. It is within 2 standard deviations of the mean, so not unusual. Okay, so use this same process to think about this similar question. A 6-sided die is rolled 50 times. The number of times that a 1 appears are counted. Out of 50 rolls, a 1 is rolled exactly 15 times. Is this an unusual number of 1s? So pause, think about this question using the same approach, and we'll talk about it. Okay, so we can calculate our mean, number of trials times probability of success in a single trial. 50 times 1/6 is 8.33. Our standard deviation, square root of the number of trials times probability of success times 1 minus p times 1 minus 1/6 is 5/6. And this will give us a standard deviation of 2.64. So the mean minus twice the standard deviation is 3.05. The mean plus 2 times the standard deviation is 13.61. So less than 3 or fewer 1s would be an unusual number of 1s in 50 rolls. More than 13, in other words, 14 or more 1s would also be unusual. So 15 1s in 50 rolls is larger than the mean plus 2 standard deviations. It is more than 2 standard deviations above the mean, and therefore it is an unusually large value.